Hi, second video today. My voice is crap like for the PSP video, but doesn't matter. This is the book. This is specification 1.1. If you turn to page 282, no, 287 in it. If you have the book, you have an example that I was like, oh, that's interesting. I need to test that. So that's what we're going to walk through the code today. We want to do a live coding because obviously I've already coded this. But let's switch over this to Windows debug mode and let's run it. So it opened up on other screen, of course. And here you see what the example is about, and you probably figure out what this is from the thumbnail of this video, is font rendering. And I thought it was a cool example. So I thought I should probably bring up this code in my OpenGL 1.2 list there, even though this is 1.1. The quick brown fox jumps over the lazy dog ABC. So we have a setup of the OpenGL like normal. We get the init, init display mode. Before we used double buffering. Now we're just using single buffering because that's what I used in the book. I'm using RGB because I noticed it didn't work because I forgot to add in that, and without it didn't work very well. Set up the window size, set the position of the window, and we create the window with argument 0. That's from the example of the book, which I guess that's just the title, so let's add in the title there. And we initialize it. We set the reshape function, keyboard function, display function, the main loop, exactly as the other OpenGL. And let's walk through the init. Init sets a shade mode of flat and make a raster font, which we will come to. But before that, we will look at the resize or reshape. Let's see, reshape. So it says that we're going to have a viewport that's 0 to our size of the screen. That's kind of obvious. And the projection mode, we're just going to initialize with identity matrix, so the matrix with just once in it. And then we're going to set up an ortho view, so orthographical. So it's not 3D, we're just looking straight at it. Which means also if I offset the text in the Z axis, I see nothing, because I tried this and I can't figure out why the text is like up front. Why shouldn't it respect the Z axis? It didn't. And that's the reason. It took me like 10 minutes to figure that out from the example in the book. I didn't see it. And then we're setting model view, which I guess we actually should load identity in it, but I think that's the default, so never mind. So let's jump to the init method. It sets up the raster font. And the raster font is using lists. First it sets GL pixel store I, GL unpack alignment 1, which tells OpenGL that data we have, how is it stored? Is it aligned on like 4 bytes or 16, or doesn't care about alignment, or how is our data aligned? Our data aligned on byte level. I don't care about anything else. Make it happen. CPUs are faster if they align on like 16 and 32, even 64. So aligning on 1 isn't great, but whatever. If I modify this example breaks apart quite heavily. So it will be as in the book. We're going to generate a list. We're going to generate 128 lists. Each list will be assigned to one letter. So go to our font offset, that's the starting list number. So from the starting list number and 128 above that, we got our characters, and we do not have all of them. I think we have 32 of them, or 24. How many Z minus A is, how many letters it is in the alphabet, plus a space. Oh, 26 it says, so we have 26 of them. I probably should have known that, right? So from I is 0 up to I is 26, we take j is a to z, of course, because that's 26 from a, or 25 from a, and I wouldn't have wrote this for like this. I would just step from a to z, but whatever, it's from the book. And we create a new list, and we went through the list in a PlayStation Portable video about how to code OpenGL on PlayStation Portable, but I don't have a video on the the OpenGL list here about lists. But list says that like the commands I'm going to execute after this, do not send it down to the hardware, just buffer it. So it just fills in the list with all the parameters of the function I'm calling, but they're not calling it down to the hardware. And then I can actually call the list, which says like, hey, everything that's included in this list, can you execute that on the hardware? And that means that we can actually have a program running on one machine, transfer over those lists to another machine, and execute the OpenGL on the other machine. And that's actually a good way to think about it, even when it comes to just a local machine. Your local machine buffer up things in the memory list, sends it down to the hardware, and then can execute the list in the hardware. So it tells the hardware, execute that list. And you can do it multiple times, meaning you don't need to send down all this data from your program down to the hardware all the time. It's already present in the hardware, just execute the list. So it creates a list. It says compile. You have compile and execute if you want to compile it and execute it directly. So it's a new list and end list, and in between here we set GL bitmap, and that's the data we're going to blit to the screen directly. We're going to write it to the image directly to the screen. So it's 8 in size, height, weight, width, I guess, and that's height, I guess. Then the next two values are offsets from the origo of the image. So if you're drawing an image, it's probably origo down here, but we might want to move that. So that's what it's doing, is actually moving the image down to, because this ignores the two first rows in the image. We will see that in the data later. And the next two are after we have a position on the screen that's called raster position, and that's the location of where I want to draw my next image. So you can think about it like you're drawing a character, then you're moving a bit and draw another character, moving a bit and draw another one, and moving a bit and drawing another one. And that's exactly what's going on here. So you're going to draw this size, we're going to offset the image this much, and after the image is drawn, we're going to change the raster position with 10 to the left. And this is the data for that character. So the first one is A, so the first offset is an A. And it goes up to Z, and here we add in space. So we have another data structure which contains nothing, a space. Let's go up and see the letters. And here also a reason I was thinking like, should I type in that live? No, because look at it. I want to type in this live. I'm pretty proud of me. I got one error when typing this in. So not too bad, and actually were quite fast to find also. But here we got the image for a space. And here we got an A. And down here we got the Z that I modified because I didn't like the Z. They had in the example, they had like this cross-through thingy like you had in old school Zs. Some fonts do still have it. I don't like it, so I removed it. But anyhow, we got the A here, and if you look at it, let's see, or maybe we should look at something else. We look at the I here. So you see the data. It has 18 here, 18, 18, and we know what 18 is. I mean, it's a 1, that's the least significant byte set, and the 8 is the highest significant byte set. So you have 2 bytes with the 2 bits turned on in the middle. So just the stem of the eye. And we have that a lot of times. And in the end, we have an 7E on one side and a 7E on the other side. So that's a bit interesting. Kind of maybe, I don't know, should it be an F in the end to actually, oops. There we go, I switched those two numbers around, but that's after the example. So I guess it's correct. So that's the I. And the A here, we also go and let's see if we can see in the data this actually is a A. So you have first bytes that are the same, are the same, are the same, are the same. The four of them are the same. And then we have one that's totally filled in. And then the same, the same, the same. Let's actually pick up the drawing tool. And see if we can draw here. So we got this, that was these here. And then we got one that's just totally filled in. And then we got three that just goes up like that. And 6, 6, 3, 7, 3, C, and 1, 8. 1, 8 we know is in the middle. And we have like that. There we have our exactly nicely done A encoded into the data here. And we can also notice that this starts with the bottom of the A up to the middle here, so it goes up there. So it actually draws the image inverted. It stores it inverted, it doesn't draw it inverted. And then it continues up there, so it continues up there. And then tells us that it's actually two empty spaces below it here. So that's those two spaces here that are empty. And that's probably the reason why it recentered the origo of the image to up here. So I'm betting that if I type a 0 here and just remove those first zeros here, I would save like 26 times 2 bytes in memory, which I guess you should do. That's 4, that's 8, that's 16, and 1 extra more. So yeah, so it isn't even aligned on a 16 border, so in memory. So it just stores extra here for no reason. I mean, if you have a small j or something like that that goes down underneath, then it would use those two rows here. And you see it only has capital letters here, so the example doesn't even include it. But someone thought about it when they created the example, like, that's too much for someone to type in from the book. Just cut it out to smaller letters. That's what I'm thinking happened here. So how do you type something out then? So let's see, we have our display function. In our display function here, we set the color to white, because you need to specify the color before you set the raster position. Because when you set the raster position on the screen, say, hey, I'm going to draw in 50-50, I'm going to draw there. Then it's also going to pick up at the same time you set that position, like think about it as a cursor position. It says like, oh, what color should I draw in? Oh, it's already set to white. I will draw in white. So if I would move this color here to beneath the raster position, the raster position wouldn't pick it up. Anyhow, that's also in the book, by the way. So we call print string, and we just dump in the string here. And it's doing something really neat here. It's using the ASCII value of the character in the string as an index into the list that we've already created. And that's why I created 26 lists, so it has one per character. And I thought that was pretty neat. So it goes in here, it takes a string. The string is null terminated, so we can get the size of the string. And then we just do a GL call lists with the size and the string itself as offsets. And to make that work, we make a GL list base. And the list base tells OpenGL, next time you call GL, call a list, apply this base number to it before doing anything. And then we have synchronized together the lists we have created, whatever numbers they became, with the alphabet. So this function can just send in a null terminated text string. And if you just call the correct lists and write them out, I thought it was brilliant. Really, really nice. Nicely done. So I needed to type this down to use it later. So let's just execute it. And here we go. And actually, for fun, let's add in some coding here. Because why not? I mean, that's a little bit what this channel is about, not just walking through what we already have. Right, so we need an image, and I have an image that's 256 times 256. And it needs an include sprite. I don't know what I called it. And let's see, I have an image here. There we go. Include image. Okay. So now I have an image. Let's draw that image also into here somewhere. So after we have played around with the fonts here, that is the interesting part. Let's move the raster position, or let's keep it the same. And let's draw an image. So draw image. So you have bitmaps. That's this characters here is up a bitmap. One bit only is just one color. But now we're going to draw an image. So we're going to draw image. I think it's called draw image. No, it's draw pixels. It's called draw pixels. And then I guess it's the size of the pixels. And it's the type. So we have RGBA, because I know the image has an alpha channel, and unsigned byte, because I know each RGBA is 8-bit each. And then we need the image data pixel data, which happens to be the data. And look, I got width and height here, so I could actually use those here if I want them. Image data width, image data height. And let's see if it draws a 2D image. Include expects file name. Oh, I was going to say something starting with an I there. What I am, but I'm not, because I found it, right? And there we go. That's how you draw images 2D on OpenGL. But let's move it so it doesn't overdraw our nice text here. Let's try 0. I'm still overdrawing the text. I don't like that. Let's try 80. That's much better. That's much better. But we have another function we need to use also. You notice everything is upside down, and that's because 0.0 is in the corner here on OpenGL, and not up here like you would think. So you have something that's called GL pixel zoom. That zooms. You can zoom. So you setting where you're going to draw something, and you can put in a zoom factor. So it zoomed it down like. So now you got just 50% of it. But what happens if you put in the negative values in the zoom? Well, it turns out that if you... Oh, that wasn't too bright of me. Let's move this so you actually can see it. And now I actually just going to move it random. Okay, that one is fine, can even be more. I will explain, just wait, I will explain. There we go. Now the image has turned around. Still not so we can see both that and the text. There we go. Now the image has been swapped around on both X and Y axis. It has been scaled down also, but it has messed up the origo. So before, we have the origo down here on the image, and the image was flipped upside down, right? So when we flip this one, we zoom it with a negative value, and then we zoom it with a negative value. It also moved the origo point off of the image. So this is 200 times 200, and I'm bloody hoping that I'm correct on that, because now we're going to reverse the zoom again, and the image should end up here. And trying to align images in OpenGL is a pain on 2D, I noticed, because of this. So just going to reverse the zoom. And see, yep. So now we have 200, 200 there, and instead of being down here, where we had the picture before, it just swapped around. So flipping images around with zoom is not comfortable. There is no GL rotate, which would be awesome. You can of course textures to polygon and rotate it, but if you don't want to do that, you don't have to. And what can you do with this? I'm not totally 100% sure actually what you can use the 2D for. I haven't used it before, I just use textures. But I guess since if you're using the old GLUT and you have the keyboard, and the keyboard sends in, oh, you have a mouse also, you have a mouse function that works the same. It sends in the X and Y coordinate of the mouse. So I guess with the X and Y coordinate from the mouse, you could render out the button, and when you hover over it and click on it, it clicks down on the button. So you can make 2D with OpenGL. Like I said, I have used other libraries to draw 2D. I haven't used OpenGL to do it, but now I have, and now you have too, because you're downloading the code and you're trying out the nice fonts, and you don't have to think about is that the copyright font or not. I mean, it could be, but it is in the specification, the book from OpenGL, so I guess that font is fine to use. Would be nice if someone could make small letters instead of just capital ones, but hey, I thought this was neat, so happy coding!